I'm going to try. I hope this works. I had prepared a presentation talking about the design of a water mist system for the National Gallery of Art in Washington, D.C. And looking through that material today, I thought, geez, this is just overwhelmingly boring. And I thought I would put a little bit of a preamble up front to hopefully put some context as to why the National Gallery of Art in Washington was interested in this.
Jeff, will you get the screen towards you? It'll drive me crazy the whole time.
Yep, I will just go.
Let's see if there's a corner. You're blocking part of the corner of the projector. There we go.
Thank you. Okay, so what I'm going to do first here is just give a bit of background as to why the heritage community is finding water mist as a reasonable option for fire protection. And as soon as we get some action.
Do the clicker by your next one. There you go. We went to.
Okay, I guess the point I need to make here is that the heritage community have some very particular objectives with fire protection. You, of course, realize they are terribly afraid of water, and it's almost unheard of that like an art gallery, the National Gallery of Art, would be interested in putting in a water-based suppression system. But they have some unique objectives. First of all, their protection objective is very high. They cannot tolerate a lot of damage to the artwork or the products that they're trying to protect, whether it's rare books or whether it's artwork. So their damage tolerance is extremely low. Their buildings that they are living in are usually older buildings. They're not code compliant. They, in some of the more remote facilities that I've looked at, there's no electricity, there's inadequate water supply, no fire service, those kind of things. So the fire suppression has to be looked at in a holistic way. There has to be some assessments of how much damage they can tolerate, how much suppression they need, and essentially it boils down to the need for performance-based design. So, water mist has appeared on the horizon as offering some potential advantages for this performance-based design approach to fire suppression systems for unique applications. And I think one thing you'll gather from my talk today is that there has to be some unique demands or needs in order to justify the cost and effort of putting in a water mist system. So there's got to be some unique objective behind the process. But water mist has come along as having some potential advantages for that type of environment. Possible to control fire, like what I've listed here, and I'm going to go through as to which one of these things are achievable and which are not. I've listed the ideal objectives for a wonderful suppression agent. We'd like water mist systems to be able to control fire better than sprinklers, meaning using less water than sprinklers. We know sprinklers are intrusive in buildings, either the pipe that has to go and be installed in the walls or the sprinklers that have to be installed in decorative finishes. They're intrusive, so we would like something that's less intrusive than sprinklers. We'd like something that would be so acceptable to the authority having jurisdiction that there would be no difficulties in getting approvals for these things. And of course, we'd like to cost no more to design and install, say, than sprinklers, or no more to maintain and cost no more to maintain and be as reliable. So that's what we would like to have. I'm just going to run through which of those are kind of achievable and which are not. Seems good to do at a time. Let's look at the claim that water mist systems are a good thing for heritage buildings because they discharge less water than sprinklers. And we know water runs down stairways and fills basements and soaks construction materials, and so it'd be nice to use less of it. Well, it is true that in general, water mist systems achieve their suppression objective using perhaps 20 to 40% of the discharge that we get from standard sprinkler systems. So that's a good thing. One thing I try to bring to people's attention, though, particularly the curators, this is a basis comparison for the amount of water discharged by a standard sprinkler system in a rare book vault. Using standard sprinklers, basically 4 sprinklers located around some burning books on the shelf. And I compared it to the, skip this out of that. I compared it to the amount of water discharged by a system that I designed and tested at the University of Maryland for the same rare book vault. And we can see that the sprinkler system would be discharging at a 15-minute discharge. It would be discharging about 33 to 55-gallon drums of water. So you imagine a big 55-gallon drum of water, and you tip that over, and you would have an awful lot of water in the rear book vault. While the water mist system took about 6 55-gallon drums of water. But the point I try to bring to people's attention is that if you're standing in your rare book bowl and you've got 6 drums of water and you tip them over, don't forget there's still some water. And this is a kind of a misconception we frequently have to dispel in people's minds that, water mist is not even going to get anything wet. I've had an odd sensation of stepping into a simulated electrical room on a ship. You've just extinguished the cabinet fire or subfloor fire with water mist, but as you step over the threshold, you've got 6 inches of water around your buoys. There's still water. So that's a point that I want to bring to their attention. How about the fact that water mist systems might be less intrusive than sprinklers? Instead of having 4-inch pipe and 3-inch pipe in the walls of the building, we might only have 1.5 inch or even 1-inch pipe in the building. And it is true that pipe can be less intrusive than sprinklers. One of the things I'll bring out with the National Gallery of Art, there are some disadvantages. There's a lot less choice in the type of sprinklers that you might want to use in terms of architectural finish and that kind of thing. And the additional care, particularly for a high-pressure system, the additional care taken for the hangers and the closer hanger spacing actually may mean that you're doing more intrusive stuff in the building than the standard sprinklers. What about whether water mist systems could be as easy to sell to the authority having jurisdiction as a standard sprinkler? Well, answer, no way. The water mist systems are a pioneering effort. Authority having jurisdictions have to be convinced, and the listings are never complete. There's a whole lot of holes in the infrastructure that supports the things that would allow an authority having jurisdiction to accept a water mist system as an alternative to sprinklers. So I don't think we can say that it requires less effort to put in a water mist system. What about cost? Well, no way. The costs are 3 to 4 times that of standard sprinklers, and that number keeps changing depending on which job you're talking about, details. They're not going to be competitive. At the present time, water mist is not competitive with standard sprinklers except under rare circumstances. Those circumstances may be, I believe there was a Marriott hotel in London that was a very beautiful heritage building, and the impact on that building of putting in a standard sprinkler system would have been very large, very destructive to the building. In that particular case, the two systems were competitive. As you'll find out, the heritage building environment sprinkler systems cost a lot more than the standard $2 a square foot you might expect for a local warehouse. So under rare circumstances, they might be cost competitive, but otherwise they're not. What about maintenance? Well, right now, there's, you've got Instead of going to 3 different possible competing companies in your local town to maintain your water mist system, you're probably going to fly somebody over from Finland or Germany or maybe in from Baltimore to maintain your system. So it's difficult to get sole source. It's difficult to get competitive maintenance costs on the systems. The maintenance procedures for water mist systems are still being pioneered. I'll talk a little bit more about that. There's a lot of proprietary expertise. The Marriott company out of Finland is not going to teach just anybody who doesn't have a signed agreement with them how to maintain their systems. So that's not going to win the day. And reliability. Reliability is not at this point going to be equal to sprinklers. It's going to be a few years before it is as reliable because it takes additional skill, additional attention to detail, and there's many more opportunities for lapses in that and things to get degrade over time. So let's look at why anybody in their right mind would put in a water mist system. And it depends on the circumstances of the particular project and the circumstances of the objectives of the end user. For example, if we look at the pros, there might be end user 1 and looks at the fact that the fire control is equal to or better than sprinklers. The situation in many applications, certainly in hydrocarbon enclosures. That the fact that it discharges less water than sprinklers might be hugely important to certain clients. The fact that the pipe can be put in and it's only 1.25 inches or 1.5 inches diameter or smaller might be very valuable to this particular end user. The fact that extra effort and the difficulty of getting the AHJ to accept it is high, extra cost to install and design, to maintain, and the concerns about reliability, they're of less importance to this end user than the next guy who comes along and says, well, we don't care about the fact that it's better than sprinklers. We're more concerned with these things. We say, no, we couldn't possibly put in a water mist system. They're seeing these things, cons outweigh for them. So I'm going to switch presentations now. That sort of just gives you some background as to what happens when someone decides they want to put in a water mist system. So, let me come along. We have the National Gallery of Art in Washington. It's a very beautiful West building, and they have a number of special hazards in that building. So the purpose of my talk here right now is to explain the design of that system and how I've tried to design the system to meet their particular needs. And it is also a case study to capture the big issues about water mist systems, what it is that you have to do to learn about them, what it is you have to do to design them and to get them into the mainstream construction world. It's also an example of the role that a specialist fire protection engineer can play, as I think a point will become evident that there needs to be a specialist fire protection consultant taking the picture of the overall fire protection and system design at a level that perhaps the design, build, and construction people will not respond. So, with the National Gallery of Art, there was in the beginning a fire hazard analysis. And the fire hazard analysis pointed out to the gallery people that although they only had barely combustible paintings with small fuel load on the walls, they actually had some galleries where they have very beautiful wood walls. We calculated the potential fire size from the burning wood in the beautiful wood wall galleries. Get something like a 10 megawatt fire, 20 megawatt fire quite easily, which would of course overwhelm the rest of the building with smoke and everything else. So the perception that the art gallery did not have a heavy fuel load in certain areas was not founded. So they had combustible ceilings and combustible walls, creating a hazard to the entire gallery. This established the need for a fire suppression system. Now the options, of course, are clean agents. Take the public coming off the mall in Washington and expose them to CO2 or Other hazards, the clean agents were not suitable for these large open door galleries. Sprinklers, water mist subject came up. Now there's one particular barrier that the heritage community, particularly the art gallery community, has in terms of that usually prevents them from using a water-based suppression system. And that is that they receive art from other galleries, international galleries. And those other galleries will have requirements in the contract. We will not send the Mona Lisa to your gallery for display unless you meet these conditions. And one of them, of course, is no water over the collection. They don't want any roof drains, they don't want any water anywhere near. So that's a major issue with the art gallery community when you start to propose a water-based suppression system. There's additional barriers to the choice of, say, water mist. Sprinklers were were considered, and of course it was a standard by which everything was compared to, and say, well, we could put in sprinklers. The other clean agents were not suitable in these huge volume spaces with open doorways. So water mist came up. They were very curious to find out what can we achieve by using water mist in these circumstances. Now, main barriers to that, of course, is that there's no other galleries that they can look at, either in Europe or in North America or South America, to point to and say, well, they've got water mist systems. So this is a pioneering, first-time effort. There's limited experience among the fire protection consulting community in designing water mist systems. There's been a lot of talk of it. There's been articles written on it. But who actually knows what they're doing and can actually come up with the design? Well, of course, we had used to fill that one. Local fire protection, inexperienced. You can't go to the local contractors and get your standard design build situation. Ordinarily, you can rely on sprinkler contractors to do the design, ongoing calculations, to get approvals, to completely understand every aspect of the job. That's absent. Who's going to bid this job, who's going to actually install it, who's got the skills to do this. There's different technology with the high pressure tubing and fittings and different pump systems. So those are barriers. But uniquely, with this opportunity with the National Gallery of Art, they're able to act as their own authority having jurisdiction. So they weren't dependent on the fire protection, the chief fire protection engineer for the Smithsonian or the architect of the Capitol or any of the other senior authorities having jurisdiction. They were out of the way. If the gallery decided they wanted to use water mist, well, they would approve it. Just about any of the major projects that I've worked on have all been on that basis. There's some level of independence of the end user. If they're dependent on going through, well, we need this approval and we need that, we can't make this decision, can't make that decision, it doesn't happen. Also, there was an opportunity because there was major renovations planned for these spaces. Everybody could go to work and rip some walls apart and get in behind places and do some work. So this water mist system could be integrated with the plan, the long-term plan for the improvement of these spaces. So this is where this begins to become a fire protection engineering consultants project. Actually, we had done demonstration fire tests, and we'd have people come in and hang art on the walls, and we sprayed water, and then conservators examine things and whatnot and get comfortable with it. But then we get to the point where, well, let's actually design a system. We're going to go ahead with this. The first thing you do is you write your fee proposal. And after you get over that hurdle, then you go to work. So meeting with the conservators and the facility managers to see exactly what their constraints were, so we understood what we're trying to do. We come up with a design to meet those needs, produce the engineering drawings, write specifications, prepare cost estimates. That's hard enough to do when you actually have some experience with the construction phase, but when there's no previous experience, it's a little harder. And then provide construction admin services and acceptance testing. So let's get into the first phase of this was to design a water mist system and put in the basic infrastructure for a system to protect two specific small galleries. Difficult to see there, but this is called the Widener Gallery. These are 15th century panels from a French, actually not a French, Italian villa, and all combustible. They're mounted on steel studs with a cavity behind there with a concrete wall around it. And so it's all basically combustible wall paneling. The other gallery is the G19 gallery, was a beautiful ceiling from a, again, I think it was an Italian vintage area. This is the driest tinder wood you could ever imagine. Get up above that. That wood is just like light cedar, like balsa wood, and extremely dry. There's electric wiring laying up above there, and that entire fire is that ceiling is what is combustible. There's marble walls and there's some tapestries on the walls, and that's about it. So the objective, say, start with the G19 gallery, was to protect the combustible ceiling in an otherwise marble space with almost no other combustibles. A couple things to note here. Ceiling height's 5.4 meters, while the nearest approval for a light hazard water mist nozzle was 5 meters. What the heck, we'll get around that one. We have about a 15 meter by 7.4, basically 50 feet by 25 foot room. 16 foot floor to the ceiling. We have a 27-inch deep space above it, concrete pockets, and working from, we're trying to stay within the tested and listed aspects of some water mist equipment. NFPA 750, the standard for water mist systems, requires that all water mist systems be based on some fire testing and some approvals to the extent that they're available, and we were trying to do that. The Marriott company out of Finland had actually 1, 2, 3, 4, 5 different nozzle options for that had been approved for light hazard occupancies. These ones were all good for 5 meter ceiling heights. These ones have been tested to about 8 foot ceiling height. And so I had a basic inventory of nozzles that were potentially suitable for this light hazard application. Now the spacing is set by the listing, and distances from walls are defined, and the K factor in metric units is all established. So I had some nozzles to select from. But of course, nozzles tested for water mist systems are generally dealing with the standard tests are some kind of furnishings on the floor. There's one furnishings in the corner. There's one furnishings in the corner with the combustible wall panels. There's nothing there anywhere to test for combustible ceiling. In fact, they all essentially are based on non-combustible ceilings. So I was on my own here. I basically took their horizontal sidewall nozzle and inverted it and tested them to see that I could get the throw between these decorative beams to wet the ceiling surface. Then then of course I had another series of nozzles that are actually intended for small spaces and ships, bilges that have a 120-degree cone and a lower flow rate, and I used them for the 27-inch deep space above. In between, these are concrete, deep concrete beams creating these little pockets. So I had the horizontal sidewalls to wet the ceiling. I have some standard ceiling nozzles in order to deal with the fire in the middle of the room. There could be a fire in the middle of the room. I had to anticipate that. So they're spaced as if they were just protecting the room, and they would have essentially been just about enough on their own to protect this room. And then, of course, the special with a number of other details I had to be concerned about. The concept of the system here, we installed a high-pressure, multiple pump assembly in the basement. I'll be talking about that a little bit. basically one motor. Each motor has 2 pumps and a chain drive, and these are little magic things I call unloader valves, which we'll talk about. They produce, it's a positive displacement pump. They can produce the 115 bar, 1,500 to 2,000 psi pressure needed. Piping system, a shut-off valve, a deluge valve. This had to be a pre-action system, so this was a special valve that could have low pressure on one side, high pressure on the other, and then release. Basically, empty piping system. And I became concerned about some of the reasons. I'll explain some of the reasons why I ended up with the. Let's go back here. Notice I have the supply coming from the basement, goes up, feeds the different nozzles. So basically, it's a 38 millimeter main, 1.5 main, stainless steel tubing. A check valve, that's a European symbol for check valve. Gets everybody upset, but insist on using it. And then I have a way to push water through to the end of the system.
Quick question. Yes. Are all those nozzles going to discharge water at one time based on detection system, or
No.
individual nozzles?
They are individual nozzles.
I just was early.
Right. Machinery spaces have open nozzles. These are thermally activated nozzles, 2.5 millimeter glass bulbs. You can pass that around. So they're just like a sprinkler.
Was there an issue if the fire happened under a beam? Say somebody brought in a piece of furniture to put on display. That's where the fire started, under the beam, where that would activate one of these sidewall heads that was upside down, but that water would cool the floor area coverage nozzle.
I set up in the testing, if I can see the ceiling here. I did a mock-up. I have that nozzle there is the floor area coverage. These are the nozzles that are in the pockets here. This wetting, it was a little tricky. I had to put these here, these in this space. I had to essentially assure that these were not getting wetted. At the same time, I was proving that I was not wetting all the ceiling. So, because I had my arrangement for the water mist, these horizontal ones was that I was essentially wetting the ceiling. And in the test I did to show that I was wetting most of the ceiling, of course I did, I would get out and wet most of this. But when I set up with some in that location, I was not preventing them from activating, and I was getting away with it. But it is as good as I could get with not cold soldering those sprinklers by having these things spray on them. We are a fire in the National Gallery of Art, and there's a failure of this. I'm sure there will be a lot of discussion on that.
Right. I'm just curious how you handled that. I mean, I'm sure it came up.
Yes, it did. I handled it by conducting more spray testing to see what my wetting pattern was, and I satisfied most of us that we were going to get away with it.
Did they actually penetrate that ceiling system?
What's that?
They actually penetrate that ceiling system?
Yes, well, actually that, I'm going to back up here. That's a hollow beam. And I was just above, in the space above it. This one actually was quite accessible. The next one over closer to us out of the photograph had a duct on top of it. I had to use, we had the curators drill the hole. And then everybody worked carefully to show that we could install. In fact, we had mock-ups, and I put that in the specification, construct a mock-up, drill the hole, get the curators absolutely comfortable with how it looks. The whole job has gone that. Every single hole that was drilled was first of all mocked up, and they became comfortable that they could allow it. But above that beautiful ceiling, of course, it requires this way and that way. And
Isn't that really, look at all that, is that's where your highest risk, the highest likelihood of having an ignition scenario occurring is up in the intersection.
That's right. And that's where I've got the nozzles nicely spaced out, and they're very comfortable with what's going to happen above that ceiling. Okay, let's move on, or we'll be here all night. Boy, I've got a lot to go through. Okay, the system concept. It's equivalent to sprinkler system. It's light hazard, customized for some unique fire problems. I'm not going to go through the step-by-step on the Widener gallery with its combustible cavity behind, but it was the same thing. Every cavity is done behind, and then very attractively spaced nozzles for the pretty part. Pump water supply, one pump serving multiple spaces. And as you'll see when I get to the cost later, this first project was very front-end heavy. We had the whole cost of the infrastructure, the major pumps, the changing the power for the, well, they didn't have 480 volt, they had 220 volt, so we had to put in a transformer. We had to then modify the emergency backup power, a whole lot of things that were cost load were put on 2 little galleries with about 12 nozzles in them. So, you can imagine that the cost per nozzle are pretty high. But the expectation was future expansion, and that's what we moved into. Pre-action systems. But previously I was fairly reluctant to get into pre-action systems, but now I sleep better every night of the week because this is a pre-action system. All my concerns about water hammer and all the other things I might be concerned about, I'm quite comfortable with the fact that these systems are, I'm not going to have a nozzle failure. Those are 2.5 millimeter glass bulbs in those nozzles. I know there have been a lot of failures of 3 millimeter glass bulbs in standard sprinklers. And again, the fact this is a pre-action system makes me feel a little bit more comfortable about that. Low pressure supervisory air, 50 psi, 3.5 bar. Takes 2 signals from 2 smoke detector signals to operate open the valve. And then takes the heat from the fire to activate the sprinkler before you ever get water.
Check on the bottom. There's a button or a clicker on the bottom.
Yeah, okay.
I don't like that.
Engineering, I was concerned about the compressed air trapped in the pipe. As you'll see, I'll have a diagram here that explains a little bit better. Of course, I have a pipe that's empty, just filled with air at 3.5 bar. I'm not going to fill it with water and create a trapped pressure bubble, air bubble in there of high pressure. And the gallery was extremely insistent on an emergency manual shut-off valve for each one of these galleries so that a security guard could open this door, close the valve if there was water coming out. Have to be advised to, make sure there wasn't a fire, but you could close that valve. And of course, if you've got air trapped in the piping system, it acts as a big spring, and it will continue to push water out of your nozzle even though after you've closed the valve. This often upsets people and gets them concerned. But I wanted to get the air past a check valve where it would not act to expel water after a valve is closed. I was worried about having compressed air in the tubing as well with the 110 bar because it's an additional hazard. If there's something, fitting fails, then there's objects that fly around the room a little bit. So I designed this end-of-line check valve concept. As we'll see, I ended up with a lot of areas potentially trapped, and I had to design a system where I could push water through with compressed gas out to an end-of-line drain. But I couldn't go into a gallery and put in a ladder and go up and start opening up. So there's no access to the galleries for any draining after this process. It's not this button or that button, it's just, okay. So the 110 bar, I'm not going to go into the accumulator system I put on to prevent direct filling with the pump, but this is full of air. When the system operates, the deluge valve opens. This is now full of water. The air is trapped on that side of the check valve and can't act on the nozzle portion of that system. So then phase 2 comes along. Now there's 10 galleries, and they're large galleries. significantly larger project. In this case, these are basically 13 meters by, they're 40 feet wide, and they're 100 feet long, and they're 22 feet high. They're quite large, combustible wall panels. We've calculated you could get a 10 megawatt fire in the corner over here. If the furniture in the middle burned, you might have about 100 kilowatt fire. So this is not the fire load, that's the fire load, and that is also the objective of the suppression system. So we're dealing with nozzles around these lay light systems, closely spaced nozzles that basically create a wall-laying effect. The way the system was structured, I basically had the pump in the basement, the risers up to the lay light level, I've got the deluge valves up there, so I have water up to this point, deluge valve. Then I have these low trap sections around each of these lay light areas. And again, using the end-of-line check valve, the pump starts, the valve opens, the pump starts, the water goes through around the loop, through the check valve, gets the air out beyond the nozzle portion, and then fills right up to the closed end-of-line drain valve. And then to drain the system, just hooked up one or two cylinders of nitrogen to a point here, and then blow all the water out through the system, and then let the gas flow on to get it as dry as possible. So the challenges here, we have general objective to meet NFPA 750, which requires that you match the fire test protocol to the actual application. And of course, you're never quite perfectly there. The fire test protocol didn't test combustible sealants, so automatically you're on to having to stick your neck out. High pressure positive displacement pump assemblies. Marioff, the company from Finland, said, well, we have the system approved by IMO on ships, but we don't have an FM approval on the system. But we'll get it. So they said they would commit fully to getting their system and their controller approved through Factory Mutual, so that by the time the project was done, the approvals would be there. And if by some chance what they installed did not meet the approval, they would, at their expense, fix it. And that more or less worked. The part that was at their expense, that they balked at that. But as it turned out, their controller did not get approved. And we ended up taking that controller out and installing a much more, a much different, absolutely different controller. Anyway, so that was a challenge through the process. And right to I think it was March 16th, we finally commissioned, this last few weeks, we finally commissioned the new pump controller. Things like main control valves, those deluge valves, are listed under IMO for certain applications, but not as pre-action valves, and they're not part of the FM approval. So there's all kinds of little things that don't fit perfectly in the box. You see pre-action valves here, have a high pressure main. You have 365 psi on this main, 25 bar up to the pre-action valve, and then we have 3.5 bar in the piping system. The solenoids here, I have some better photographs. Here's the pre-action valve to the new systems. Ball valves that don't quite match what you're used to for supervised valves. So of course there's a hole drilled in there with a loop and a way to supervise it. The solenoid to release this valve, and then we have basically the system's pressure transducer there, and all those signals brought back, everything being supervised. For the galleries, the 10 additional galleries, I've got actually 6 systems. There's 4 of them here protecting the bulk of the galleries. And it's all kind of modeled after piping systems I've seen in Alaska. I won't get into the details of all that. And let's see. Different things. This consists of 4 27 kilowatt motors as pumping assembly. The building was equipped with 220, and we had to put in a transformer to get to 480. There's, for high pressure water mist pumps using positive displacement pump concept, they need things called unloader valves, which I'll talk a little bit about. Here's the pump assembly in the basement. 1, 2 motors on this side, and there's 2 around the other side. There's 2 pumps per motor. These are the small pumps. They're about 13 gallons per minute each, 49 liters per minute. And there's each one has its own unloader valve. There's an unloader valve. Here's 2 unloader valves. There's an unloader valve down there. So an unloader valve works to, because it's a positive displacement pump, it's trying to push a piston of water out of the chamber. And if there's no place to push it to, then either the motor will burn out or something will break if they put the pressure extremely high, it'll blow a ring or something, and you need to get rid of that water. While an unloader valve, if the system pressure is higher than the setting of the unloader valve, it will open up and let the water from the pump bypass. So you end up with what's good about this system is that you can match positive displacement pumps, which have a fixed output, to a variable demand system. If 1 nozzle opens, 2 nozzles open, 3, 4, 5, 6, 8 nozzles open, there's a variable demand. So how do you match a positive displacement fixed output pump system to that? Well, one thing is to use several small pumps, each with its own unloader, working nicely with it in a nice comfortable range. Say these unloaders are good for 2 to 20 gallons per minute. That's perfect for these sizes of pumps. So you've got many small pumps, small unloaders. The system will kind of like glide up with the demand and adjust itself to a variable demand rather nicely. You can use one huge pump and one huge unloader valve, but then you're trying to supply one little tiny sprinkler with a great big pump, and you've got an unloader out of this pressure relief valve sort of fluttering away, putting out a very inefficient performance position. This is the ISO symbol for an unloader valve, basically adjustable setting. And when the system pressure is higher than this setting, it will force this valve to open and let the flow from the pump go out to the bypass. And you wouldn't believe the fun I have with these unloader valves. I'm still, to this day, going through a learning curve. I'm sinking as close to a Frumious Bandersnatch as I'm ever going to get. Let's look at the hydraulic multiple pump system. Positive displacement pump curves, if you have one motor with its 2 pumps, you get about 100 liters per minute. So there's one motor, one pump. And we have a demand out here. I'll tell you that we need 2 motors and 4 pumps, 3 motors and 6 pumps, or 4 motors and 8 pumps is getting us up to the point where we're beyond our operating point. So that's how we figured out we needed 4 motors, 27 kilowatts, we knew the pressure we needed, and this line is, here about H max is 115 bar. If you take the Q and the D, and you calculate the horsepower, or the kilowatts required, you get a certain maximum possible pressure for a given power in the motor. And so that's what the H max is. So that's calculated as the maximum capacity of the motor delivering its full Q, and that's as high a pressure as it can get. But then that is usually mitigated by the setting of an unloader valve which would be below that. To test this system, it's not quite as clean and neat as testing your centrifugal pump, which you've all probably done and are utterly comfortable with and completely able to get confident results out of. This is a little bit trickier. Of course, you've got a programmable controller that's doing all sorts of little things that keep surprising you. We've got unloaders that are setting to the nearest 7 bar. So you've got quite a bit of variability in those things. And then to test this thing, it's not like you can just put on a bunch of hoses and measure what the Q is and plot the point. You actually have to set the K factor for your discharge so that you can actually get your point. So I've skipped about 30 slides here, but here's the latest flow test. And this defines the challenge here. Here's our design point. I have, this is the setting we set the unloaders at, it's 110 bar. It's less than the maximum possible output from the pump. We tested one motor and its two pumps, and we got a flow and pressure very close to what we would need, up to the 96% of that condition. Then we tested with two motors operating and got that flow and various playing around with the throttling and the back pressure and the K factor for the discharge. We got that point. We got within 97% of that. Somehow with three motors, some of the unloaders were just a little out of sync or something, and some water was being unloaded that we didn't want to be unloaded, and we could not get to that point, so we got within 87% of that. And then with four motors operating, we end up here about 91% of the target. Theoretically, if I buy a pump with motors and Q and RPM and everything else worked out, and I want 400 meters per minute at 110 bar, I know the motors are set for it, I'd like to get to that point. But I'm not happy with this point. And I just did a test 2 weeks ago, testing the pre-fill on these pre-action systems. I designed an accumulator system into it because I didn't want the pumps all starting to fill that pipe, that empty pipe. So I used a gas nitrogen cylinder plus 3 bottles of water that could fill the system to about 40 bar, prevent the pump from starting, and nicely. But for various reasons, the panel was programmed incorrectly. So instead of that operating properly, that didn't perform well. So the next test, instead of doing that, everyone in the room except me decided that they wanted to do a test without the accumulator. So we did a test of the next system without the accumulator. And for some reason, it went up to 130 bar. And yet we had methodically and painstakingly set everything at 110 bar. So then the pump rep says to me, oh, did you know, well, we set those unloaders under flowing conditions. It's completely different under non-flowing conditions. And of course, we're testing when we fill the system under non-flowing conditions. And I said, well, how come we're 3 years down the road and you didn't tell me that before? You know, so I'm still going through a tremendous learning curve with these things. And I'm a little ticked off about that. As far as I'm concerned, there's no reason why that should have happened. Anyway, lesson learned. Unloader settings are tricky. They should be set in a hydraulics lab, and even then, I'm not sure what you're going to get. There's unavoidable variation, so you'll never get a nice pump curve like you do in centrifugal pump, where you've got the factory line, and you get this nice line just above it usually, and then you feel good about the pump test. You're never going to get there because your unloaders are too sloppy, and you can't test to the max anyway, because your unloaders have to be below that max. So there's probably some more learning to do on how to evaluate these systems. I'm just a little bit nervous, but we've tested the thing enough that I guess I'm pretty confident that what we're delivering is more than the maximum demand of the system. That's the point of which we're so excited about it. We need to design the test header. Actually, it's got to have specific K factors. And there's all the controller logic, programmable controllers, and one Navy job I did with variable speed controllers are very different, quite interesting to test. Specifications. The sprinkler contractors who were going to install this job had no experience whatsoever with water mist systems. So I wrote a very in-depth and detailed specification to provide everything I thought they could possibly ever need in terms of knowing how to design the system. I put in all the water mist system design requirements. I put in tables of all the spacing. I just basically reproduced your NFPA 13 and put it into the spec. I put in the details on the hydraulic calculations, how they should approach that. I even developed tables of equivalent lengths for the different types of fittings. The fittings for high pressure, I didn't bring one because it weighs too much, are not at all like standard sprinkler fittings. So you can't just go to NFPA 13 and say, oh, 1.25 inch T, I'm going to add 5 feet. So I've developed tables for that. Put it all in there so that they can do their calcs. There's the products, tubing, strength calculations on piping, where you can bend Schedule 40 pipes, stainless steel when you can, and what effect it has on your working pressure. I put all of that in there. All the requirements for minimum bend radius, all details of how to operate compression fittings and how to get training on all of that ahead of time. Cleaning and swabbing. I have a gun with a pellet of foam in that you use compressed air to blast this pellet through the pipe, and you have to do that until you've got clean, no little bits of metal in the pipe. Put it all in the spec. So, lessons learned. I guess one thing I learned is that the installing and doing the tubing bending and doing neat work and beautiful bends and aligned pipe and whatnot is get a good sprinkler guy who's willing and wants to make an issue with that, you can get some really, really nice work. I think the sprinkler contractors, the right foreman, and the right guys can do nice work. Hydraulic calculations, you got 2 contractors in this. The first phase was done with the contractor who spent all the money learning about this stuff and trained the fitter. And then he didn't get phase 2, and the fitter quit to him and went to work for the second sprinkler contractor. So the second sprinkler contractor had very experienced foreman for the product. But they got very good. Hydraulic calculations, one contractor was not paying attention to details. I noticed the second contractor just did a beautiful job with the hydraulics. Labor for hangars was 3 times more than expectation, at least it was on the first project. One thing about this intrusion on the building, people think, well, water mist system, small diameter pipe should be a piece of cake to install. Well, don't think of it, please, like the standard 13D sprinkler system where you stick some flexible pipe into the attic joist and you don't worry about anything. The work involved in spacing, hanger spacing, 7 feet. Look at the structural, these are basically trapezes that span from this bottom flange of this beam to an angle iron on over here. These are the tube clamps, tube clamp, tube clamp, tube clamp. Tube clamps had to be so far from each major T. Beautiful bending work and a lot of money spent on hanger connections. Cost. This was the first major water mist system in North America. A learning curve for the sprinkler contractors, and even for the vendor, the Marriott, the Finnish company, had never done anything on this scale before. And none of them had ever done anything with me in the background watching every move they made. So the costs of that were about $50 a square foot for the areas protected. Very small galleries, huge cost for the pump and the infrastructure. By the time we added phase 2, and you now blend the whole thing into basically 12 galleries, many, many kilometers more of tubing and pipe, now cost comes down to about $30 a square foot. We must remember that a standard sprinkler system in that environment is not like your normal warehouse, which might be $5 a square foot or something. It's typically $12 to $15 a square foot, so or actually can be higher. So this is about 2 times the sprinkler cost in that particular environment. And that cost will be coming down. That will vary all over the place. There could be some small heritage buildings in which you use a 15-minute protection gas-driven pump system that don't require electric power, and you don't need to dig an underground and bring in additional water supply. It's all self-contained, pre-engineered system. That might be pretty cheap. So these numbers are, for this particular application, it's going to vary, but it's not going to be competitive to sprinklers for some time. Biggest problems, Authority having jurisdiction, knowledge level, particularly for on the National Gallery of Art, of course, they could act as their own authority having jurisdiction, and they were very interested and they were willing to make engineering decisions. In the state of Alaska, they have a very willing and state fire marshal's office, and they basically have made a point of accepting water mist systems and the machinery space modules and such as that on the north slope. So they have a significant knowledge level. But you go to it, you can't just walk into the state of Minnesota and go to the fire marshal's office and plop down the set of water mist plans and get it approved. Not easy. So everything takes time. Estimating. I'm not sure how those sprinkler contractors estimated their job. I know they underestimated the labor for the hanging. The first contractor took quite a beating, helped them out in various ways. I don't think they completely walked away from it suffering too bad, but the estimating is the key. You got to be really careful on understanding the labor and the materials that go into that. The specialists like Marriott of Finland or Fogtech of Germany or Tyco in Rhode Island, they'll have some specialists who know everything about their systems, but they're not the guys working with the local contractor. Very often the local contractors bought his equipment from the vendor, and the vendor said, yes, we promise we'll come out and help you with the whole job. But actually at the 11th hour, they're not there. And the sprinkler contractors doesn't have the knowledge to even know how to tear down a valve or make something work. Some of them now do. They can tear down a valve on the spot and make it work, but it's just a transfer of knowledge needed there. That's not right there yet. Engineering supervision, I won't even say what my fees were. The engineering supervision is an additional cost on that. I got to get through this. It's too slow. National Gallery of Art is indeed pleased with the system, and they're showing it off to everybody. This is a credible group in the heritage community, so there's an awful lot of attention coming from other galleries now. And we have sprinkler contractors in DC able to work that in. There's a project going in at Dulles Airport with the sprinkler contractor who's doing the National Gallery of Art work right now, is working with Marriott on the Dulles Airport system. So there's now a growing body of skilled tradespeople. And there are specifications out there. So that is maybe where I should leave it and take some questions.
Not a question, but maybe more a comment of information thing. Electric Scientific Company is the local Marriott authorized distributor, and if anybody would like to see, they do have a CD that actually shows a suppression of a fire aboard ship, which is one of the areas that they really got started on.
Right.
And we'd be happy to make that available to help anybody with any questions.
Right, that's great.
They do also have pre-engineered systems. I agree with everything you said. That's what we've learned so far. Looking at the jobs they've done, the engineered systems, it's a much bigger thing than even when Halon first came to the marketplace. Much more complex.
Right, unfortunately so. I think it's got a ways to go to get easier. But the pre-engineered systems for turbine enclosures up to 260 cubic meters, and those are manageable systems, and there's no big mysteries. They meet there within, if they're installed within the approval, that works. I run into things though, not with Marriott, because unfortunately they don't have one of these cycled systems. But there are, I think Fike and Chematron have systems that are, and Securaplex also in Montreal, that had a twin fluid system. They have cycling systems used in their turbine enclosures and machinery space that would operate for something like 220 seconds, 40 seconds on, 40 off, 40 on, 40 off. And for various reasons, that's a good way to help put out a fire, because the room gets a little bit hotter, there's more evaporation, and you can actually extinguish a fire faster by cycling than you can by just running the water all the time. However, they would go to 220 seconds and then stop for 3 minutes. And then at the end of 3 minutes, if the detectors indicated that there was still fire there, then it would operate it for another 220 seconds. And they called that whole thing 10 minutes of protection. When they started installing those in the North Slope, they were approved for 260 cubic meter spaces. They were putting them into 500 cubic meter spaces, or, God forbid, 1,200 cubic meter spaces, and still using the same cycling operation. Well, what happens when you get into a larger volume space, when you're trying to work with a total flooding water mist system, where you depend on the enclosure to trap the heat, and for the fire to consume some oxygen, and for the heat to evaporate the water droplets and create water vapor. As you raise the temperature of the compartment, you raise the amount of water saturation that can be that is in water vapor phase, and your oxygen concentration comes down. So when you have a total flooding water mist system, if your compartment gets bigger, it takes longer to get the oxygen concentration down. So you don't extinguish the fire in 219 seconds like you might have done in the 260 cubic meter enclosure. It might take you 600 seconds if you're in a larger volume space. But they were taking those systems designed and approved with the cycling for 260 cubic meters, putting them in as engineered systems in other spaces without any consideration for that. Basically, the systems that I was brought in to evaluate, I had to say for a hydrocarbon fire in a space where the flame is exposing 1,200 PSI, methane gas piping and flanges and pump lamps. I don't want flames raging in there for 3 minutes unsuppressed. And I had to eliminate the 3-minute downside. But a pre-engineered system installed within its volume listing is going to be pretty straightforward and pretty safe to install.
I forget which phase it was, but you had the deluge valve was up above, so you had water on a main riser coming up. Was that done from a water delivery point of view, in terms of time, or was that to do with the cavitation that you talked about, or why did you do it that way? And did it take some convincing to the owner to allow that, to have the water piece?
Let's see. Well, my major concern with the pre-action system, the system is going to fill in easily about a minute. The systems have volumes that are quite small, like 100. These systems were around 100 liters. The other systems are more like 200 liters, the larger systems. But now the pumps deliver, if one motor starts, and it's trying to deliver basically 100 liters per minute. Theoretically, it would take the first motor a minute to put 100 liters out to fill the pipe. But of course, because the pressure is down for some time, the next motor, after a 5-second delay, it starts, and then the next one starts, and then so basically within about 16 seconds, all 4 motors and all 8 pumps start. And of course, at the end of 50 seconds, that pipe is full of water. So it's not a delay of water getting into the pipe that was a concern to me. It was an issue of you got the positive displacement pumps that are going to go ramp up 1, 2, 3, 4 motors, bring on, start moving water, which is now moving ahead into an empty pipe, and that's going to reach the end of that pipe and that check valve, and it's going to compress the air into a fairly small volume, and then it's going to go up rapidly to about 110 bar, I thought, and then motor valves are going to start opening to relieve it. So I started to envision just a lot of shock on the system and a lot of adjustment when the thing got up to the unloader settings, and I have unloader valves operating, and I have a second pressure relief valve on the system if things go higher. I didn't, for various reasons, did not want to have all 4 motors start up and hit that gallery, and every other deluge valve in the building is going to see it as well, and come on, bring it up to basically 1,800 PSI as it came up to recent test, and then go in and shock that system. So I designed an accumulator pre-fill for that would fill the piping with, bring it up to about 30 or 40 bar, and then what's supposed to happen is that the alarm panel says, trip the system, it opens a valve on the unloader on the accumulator system, and that allows the accumulator to start to pressurize the common main down here. And then 2 seconds later, when this valve opens, the pressure's already there, the accumulator goes and fills the system. This pressure never drops below the start point for that pump. And the accumulator brings it up to about 30 or 40 bar, depending on the volume of the system. And I never see the same, I have the same Q flowing into the system, but I have gas driving it, and I have gas compressed ahead of it. My calculations told me I was having something that was going to give me less impact on that system. And because I'm concerned about a failure in the National Gallery of Art, the first system in the country, I took the precaution. Now, is there any resistance to that? Well, there's huge resistance to this accumulator system in the building. First of all, it's an additional complexity. I've got to add a slow process to fill each accumulator, each of the water volume in each of the tanks. To test the system is slow and laborious. To monitor the water quality each year is costly, and I've got the additional solenoids that have to open. And then I discovered a terrible thing in the first phase. My accumulator filled the piping system to 50 bar. The nozzles need a minimum of 80 bar to operate properly. That's the listing for 80 bar. But there was enough water left in my accumulators and enough gas that it was operating that nozzle at 50 bar for 10 minutes before 50, 40, 30, down to 17 bar when the pump would start. I was running the nozzle for the whole event of the fire at well below the necessary pressure. That was an unexpected discovery during the test. Trip the system, we pre-filled it, didn't start the pump. Okay, now let's start the flow. Now we see the pump start and go through all its operations. But we opened the system with one nozzle flowing, and the pump didn't start. And the pump didn't start, and the pump didn't start. And so by then I realized I had a problem. My accumulators needed not only a pre-fill release, but I needed a post-fill residual pressure release to dump the remaining residual pressure. So at this point, I've lost the confidence of the National Gallery of Art in terms of adding and growing complexity of the system. So right now, everybody has almost convinced me that we don't need the accumulator. Just let the system operate on the pumps, and it's great. If this was a machinery space on a ship, I wouldn't have a single second thought about it. The system's tested to 170 bar, and the system is fantastic. Strongest not going to blow apart on me, I don't think. But I didn't want to unnecessarily expose it to that. But now I'm going to have to back off of that. The complexity of the system has intimidated just about everybody. And the last person standing wanting that accumulator.
Is the water filtered, or is it just standard domestic water? Or do they have any concerns about minerals and the harbor?
Good question. The water that goes into the pumping system is filtered. And the water that sits in the accumulators is not, it's filtered when it goes into the accumulators, but it's not filtered when it comes out of the accumulators. And under certain circumstances, you can get some algae growth in water in confined cylinders, and you might have a problem with water from the accumulators. That happened in Alaska on a system where the water reservoir, all the water is filtered going into the reservoir, which is not on a Marioff system. It was filtered water went into the reservoir, and then algae growth in the reservoir occurred, and that was then the first trip test they did in about the second year of the system. They, of course, plugged everything up with algae, just like no system whatsoever, no fire protection. Because of algae growth in the reservoir, and you filter in, but you don't filter out. Well, Marriott's primary ship pump unit has what they call a brake tank on it. They have water comes into a tank, and then it comes out of this tank into each of the pumps, which is great. It's a nice, convenient way to do it. But because of the experience in Alaska, I was worried about this water sitting in the tank, possibly getting algae growth in it, and there's no filtration afterwards. I noticed at least, I think it's Chematron, they have a tank, and they have a strainer on the outlet of the tank. It's a very smart thing to do. If you get a higher pressure system, you can't put strainers and pull them apart. Those things go wrong. You can't put filters either. So I took the brake tank off of this system by running through a 100 micron filter, well oversized to handle the full flow capacity, go through the 100 micron filter into the pump system, and straight out. So I have fresh water from the city filtered going into the system. The weak point in my system is the water in the accumulators that it's very unlikely because it's a closed environment, less likely than in the reservoir that it happened in Alaska, but I have that potential weak point, and it could have algae growth in that water, which would then be a complete catastrophe for osmosis.
Where are you using this in the airport?
At Dulles Airport, I believe there's a metro train comes into Dulles, and the concern is a fire on there's a fire on the train coming into the station is what they're worried about. So there's a water mist system built along the perimeter of the loading dock or the platform beside the metro train that comes into the space. And there's some spray above to provide cooling as well. That's as much as I know about it right now. It has to do with that threat of a burning vehicle coming into the station. I believe Marriott has done a tremendous amount of work with the Madrid Metro. They have systems installed on all of the individual cars, and they have systems installed in the electrical transformer bulbs and various things that have to do with the Madrid Metro.
What's the advantage of the water system in that application versus the fire sprinkler system? For the units that go on the trains, pretty hard to have a standard sprinkler system on the train. These units they're a gas-driven pump unit, so you have nitrogen cylinders driving a piston. It's like an old steam pump. This is on the train.
Those are the first ones I'm describing right now. They're right on the train. So they are suitable to be installed on each rail car and provide fire protection within the suppression within the rail car. Standard sprinklers couldn't do that. The many little small spaces like elevator, machinery spaces, small transformer rooms, standard sprinklers would not. The advantage of the water mist there is that it's a self-contained, pre-engineered system that can be installed to protect individual little spaces without having to put in the infrastructure of mains and sprinkler the whole station. In terms of the office spaces, I was in one set of offices in Madrid Metro headquarters where it's sprinkled just as a standard sprinkler building. All of their where all the operators are sitting with their screens and keeping the metro running. That's all tile ceilings and water mist nozzles. And there the advantage is, while Madrid Metro has the staff and the experienced people with the maintenance of them, they now have the systems everywhere. So it's just as well for them to use the water mist system as to have additional sprinkler systems. And primarily less water requirement, lower water requirement than the sprinklers. I would suspect that in that case, the cost of the installation for their standard computer working spaces is competitive with sprinklers because of the fact of doing pretty large areas with the same system they use on cruise ships, and have a very low water demand. I have another presentation here, if you're willing to stay another hour, on comparing, let's say, for some heritage properties where you want to look at small rural type 18th or 19th century treasured farmhouse or something. There's no local water. The building is used for, it's basically a visitor center. It's some charming spaces with some furniture in it. It's a light hazard application, except they've got an archives for the whole county of dating from, 1714 or something in the basement of this place. So you have actually a ordinary hazard fire load in certain areas. And the water mist systems, although it's great, you don't need the electric power perhaps. You would need to run a pump. You don't need an above-ground tank that you would need for sprinklers. With the water mist system, you don't need to perhaps dig a trench because you can have a self-contained building units providing, say, 30 minutes of protection inside the building without having to dig a trench in from a common water supply or water tank for sprinklers. Many of those sites you cannot dig in the ground because it's heritage property and you don't know what's in the ground and they won't let you just dig a trench. So because of the constraints on the property, it can turn out that sprinklers would be by far the best way to protect that space. You could get an hour's protection. You could handle the ordinary hazard fire load as well as the light hazard fire load, and it would probably cost you a third as much as the water mist system. But because of the can't dig, can't put up a tank, don't have electric power, can't do this, can't do that, then you're in the position where the water mist system giving you 20 minutes of protection is the next best thing. I have additional nozzles here if you're interested. This is one from Kitty, Douglas, Germany, and I used that system and that nozzle. They tested that nozzle in some fire tests I did in New Zealand in the electrical tunnel, and that has extremely fine, almost like horsehair diameter orifices. Extremely fine orifices, very low flow rate, very nice atomization, and it did better than any other nozzles tested in those fire tests in terms of meeting the temperature control requirements. And yet, it didn't win the contract because the nozzles were twice as many per meter as the next one up, which didn't do nearly as good a job of controlling the temperatures, but was spaced farther apart, therefore fewer nozzles. And so the calculation for the project is done, well, I need 10 kilometers a tunnel, I need 1,200 nozzles, or 12,000 nozzles versus 6,000 nozzles. So, but that little nozzle did wonders. So there's, the point of passing these around is just to indicate that there are different types of nozzles and getting to atomization. This is Tyco's first machinery space nozzle with a little cylinder and a little 3mm hole in the center. That's the water mist systems come in low pressure, intermediate pressure, and high pressure. Low pressure, Secureplex, for example, was a low-pressure twin fluid system. Can get excellent atomization. Had its own problems with having to provide air and water and whatnot. Generally, you find with the Tyco systems, you kind of get up into that intermediate pressure above 200 psi, 200 to 500 psi, and then and even some of these you'd call a spraying systems company single orifice spray nozzle that's Jerry Back used in machinery space tests and Coast Guard testing. It's just a single orifice, nothing fancy, kind of good around 200 psi. So, designing the water mist system, you've got quite a bit of, you've got quite a few decisions to make as to what are the pros and cons of working with an intermediate level pressure pump versus going to high pressure. You you get to practice your pump calculations and your motor calcs. Any other questions?
Our chapter did pick up the expenses for Jack, but we appreciate his time traveling out here and spending the night with us here. We have one final meeting for the year, and that's May 26th. We're going to tour a brand-new fire museum that Tom Brace has been involved in. That's in northeast Minneapolis, so that'll be May 26th. That's it.